Okay. All right. So today we are going to go over the Earth Layers Research Part 3. So to get right into that, so the first question, which layer is the thickest? That would be the mantle. So you have the crust out here, then the mantle, then the outer core and the inner core. So the mantle is the thickest. Then the second part of that question, which layer is the thinnest? That would be the crust. So the crust is the thinnest layer. So it's just the very outer part. I've heard it in relation to the thickness of the crust to the size of the Earth. It's fairly similar to the thickness of an eggshell to an egg. So it's really not very thick, considering the size of the Earth. The next one, which layer is the warmest? So which layer has the highest temperature? That would be the inner core. So as you get deeper into the Earth, each layer is warmer than the next. So the very hottest temperature, the warmest temperature, would be at the very center of the Earth. And then the coldest layer, luckily for us, is the crust, because we live on the crust, and as humans we prefer a pretty narrow temperature range as far as what we like to live in. So the crust is the coldest layer. The next question, using your understanding of density, explain why the layers of Earth are in the order they are. So think about the Diet Coke floating and the regular Coke sinking in water. Basically, it comes down to density. Whenever there's anything to do with the layers of the Earth, density is the main cause, the main thing that they've made the layers form the way they are. The most dense materials sank to the center when the Earth was melted. So, the iron, the metals, obviously not all of them, but a lot of them, most of the majority of them, sank to the center because they were the most dense materials. Then from there, it was less dense and less dense and less dense. The next one, how do seismic waves, which are the kind of waves produced by an earthquake, how do seismic waves help scientists understand the layers of the Earth? They act like an X-ray. So this is a picture of an X-ray. So if you injure yourself and the doctor thinks it might be something with a bone, or you may have broken a bone, you can have an X-ray, which allows a doctor to look at the bone without actually, cutting your skin and all that, to look at the bone. The seismic waves are kind of like that.
I like this.
What?
Fire ass enemy. Fire ass enemy.
Okay. Was that a question?
Oh, yeah. No. Yeah. Is this like? No, man.
Oh, okay. Sorry about that. I couldn't hear you. Because scientists know how these seismic waves move through the Earth, how quickly they move through different materials, all those sorts of things. When seismic waves move through the Earth, then they can, kind of figure out what's underground and what's down there, even without actually looking at it. They can figure out what's going on down there. The next one, where does the heat, oh, there's a bug flying around. Where does the heat found inside of the Earth come from? So a lot of it is heat left over from formation. So when the Earth first formed, there's still heat left over from that. Just like if you cook something in the oven, the center of that's going to stay warm for a while. Now eventually it'll cool off, but for quite a while the inside is going to stay warm. There's also radioactive decay. So there are radioactive materials in the Earth, and they're decaying and breaking down and giving off radiation. So the inside of the Earth is hot because there's leftover heat from when the Earth was formed, and there's radioactive material that's giving off radiation that's keeping it warm as well, that's giving off heat energy. All right, the next one. What are the two most abundant elements in the crust? And then what's the total percentage of the crust that those two elements make up? So oxygen and silicon are the two most common elements. Now, if you use different numbers, your numbers will be a little bit different, but they should be pretty close. But if you take these numbers, so oxygen at 46.6%, silicon at 27.7%, add those together, that gives you 74.3%. So like I said, your numbers should be pretty close if they aren't exact. Or if you need numbers to use, then you can use these. That's up to you, whatever you need to do with it. But the big thing is that oxygen and silicon are the two most common. And when we start talking about minerals, we'll see why that is. We'll see why those two are the most common, or one of the reasons, I should say. All right, so the next one, where is the deepest mine in the world, and how deep is the mine? And then number 8, what's the deepest that humans have dug into the earth? So the deepest mine in the world is this, I'm guessing, Punning gold mine in South Africa. And it's about 4 kilometers deep, so about 4,000 meters deep. But the deepest that humans have ever dug, so just drilling into the earth, not actually, having a person there, is about over 12,000 meters. So in feet, that's about over 40,000 feet and over 7.5 miles straight down. And that was in Russia. They're not drilling anymore. The project has been shut down. Okay, the next one is it's that table at the bottom of the page. So different types of crust, and then average thickness, average density, average age, and then the rock composition. So this one, I didn't really put the averages on there. Excuse me. Because depending on where you find your information, the numbers might be a little bit different. But the first category is thickness. Kind of the main thing to remember about that is that continental crust is much thicker than oceanic crust. So we have oceanic crust about 5 kilometers thick or so. The continental crust, could be anywhere from 5 to 70 or 80 kilometers thick, especially if there's mountains. If there's mountains at the top, then it's also going to be thicker. So it just depends, but the main thing to remember is that continental crust, which is basically land, like the continents, that's going to be much thicker than oceanic crust, which is under the ocean. The densities are pretty close, but oceanic crust is more dense than continental. So continental has a density of about 2.7 grams per cubic centimeter. Oceanic crust has a density of about 3 grams per cubic centimeter. So oceanic crust is more dense. And that's because it has different minerals in it. and it makes it more dense than continental. But both continental and oceanic are less dense than the rocks in the mantle, which you would expect because the crust is above the mantle. So the mantle rocks are more dense. That's why the crust is above it. And then the average age. So the Earth is about 4.6 billion years old. A lot of continental crust is about 4 billion years old. Oceanic crust, however, is much younger. And some of it is much younger than this. I mean, some of it is brand new. Some of it is just being formed. But the thing to remember is the oceanic crust is younger than the continental crust. And then the dominant rock composition. When we talk about composition, what are we talking about? Anyone? If we're talking about the composition of something, what are we talking about?
The nature of something, maybe?
Yeah, kind of. It's what it's made up of. Like what are kind of almost like what are the ingredients? So if I was talking about if this was a chocolate chip cookie, and I was talking about the composition of a chocolate chip cookie, it would be chocolate chips, sugar, flour, butter, eggs, milk, the things that go into it. So when we're talking about different rock compositions, it's the same kind of thing. Granitic composition, it has a certain set of minerals that make up rocks that have granitic composition. Now, it might not be all the minerals, it might just be some of them, but there's kind of a set of like a group of minerals that make up those rocks. Basaltic composition is the same way, it's just a different set of minerals. It has some different stuff in it. And because it has a different composition, then it's kind of its own, separate thing. So basaltic composition tends to be more dense because it has more metal in it. It tends to be darker in color. So those are the two main types of composition. And probably the most familiar rock with granitic composition is a rock called granite. Maybe some of you have heard of it. They use it a lot in like really nice countertops or headstones, like in cemeteries and stuff. That's what they make headstones out of now is granite. And then probably the most common rock with basaltic composition is a rock called basalt. So their names are pretty close to kind of the most familiar one in that group. Right, the next one, number 10, describe how parts of the mantle move and how that moves the Earth's crust. All right, so this one is a nice just 2-word answer. It's convection currents. So this is an important one. Convection currents are something that we'll see again and again. We'll see it when we talk about plate tectonics, volcanoes, earthquakes. This concept affects ocean currents when we talk about the atmosphere and weather and air movement. With convection currents, hot things rise and cold things will sink. So like in this drawing, rocks in the mantle that are heated up by the core will rise. And as they rise through the mantle, they hit the crust, and then they can't go any further because it's the crust, so it spreads out. So it goes in either direction. As it does that, it starts to cool off. And then as it cools, then it starts to sink. And then it gets heated up again, and it rises, and then it cools. So you have this constant current. And what happens is right here where this ridge is the convection currents will pull apart the plates. I mean, very slowly, but it will pull those plates apart over time. So convection currents are very important, and it's the main force that moves tectonic plates and causes continents to move. So that's a big concept, is convection currents. Like I said, warm things rise, cool things sink, and that's all because of density. Number 11, what is the relationship between the outer core and the Earth's magnetic field? The moving liquid iron that's in the outer core produces the magnetic field. So the outer core generates the magnetic field. It makes the magnetic field. Because it is liquid iron that's moving around the solid core, that's also metal, it generates and produces this magnetic field. If we didn't have that magnetic field, none of us would be here. Nothing would be here. Because the magnetic field protects us and protects the Earth from radiation from the sun. And this is just a little animation that shows, it's just animated, but it kind of shows the magnetic field as it kind of deflects and protects the Earth from radiation from the sun. Now, you can't really see the magnetic field in real life, but scientists have determined what shape it is and things like that. So it just kind of shows that. The next one, how do scientists estimate the temperature in the core? The melting point of iron. So we know that the outer core is liquid, and we know that it's mostly iron. Well, we know the melting point of iron because we work with iron. Here on the surface, we make all kinds of things out of iron and steel and all that. So we know the melting point of iron, so we know that the outer core, it has to be, above a certain temperature. It has to be greater than the melting point of iron. Otherwise, it couldn't be liquid. It would just be solid. So, we might not know the exact temperature of it, but we know that it has to be at least, this amount, at least this temperature. So that's how we know that. Number 13, how has Earth's core changed in the last 4.6 billion years? It's slowly cooling. So, the same way that if you cook something in the oven, you take it out, and you put it on the counter to cool, it's going to slowly cool down. And eventually it will come to an equilibrium with the room temperature. It'll be the same temperature as the room, but, that could take a while. And part of that depends on how much stuff there is, how thick it is. It just depends on several things. But the Earth's core is cooling slowly. It's, getting cooler. It's not as hot as it used to be. And then the last question, what will happen to the Earth's core in the future? Eventually, in the future, the outer core will freeze and become solid. So normally when we think about things freezing, we think about water, because that's what we're most familiar with as far as something that freezes and melts and things like that. But with things like metal, since freezing by definition is just something changing from a liquid state to a solid state, a metal could be thousands of degrees and freeze, just because it's, at that point it's cold enough, or the temperature's low enough to where it becomes solid. So with the Earth, when that happens, when the outer core gets to the point where it's cold enough to where it freezes and becomes solid, then the Earth will not have a magnetic field to protect it, and then the Earth will not have anything to protect it from the radiation from the sun, and the radiation from the sun will pretty much wipe out everything on Earth, pretty much. And that's what a lot of scientists think happened to Mars, was that because Mars is smaller and Mars is further away from the sun than the Earth, it cooled down more quickly, its core froze. So then there was no magnetic field to protect it from the sun's radiation, and the sun's radiation just wiped out everything on the surface of Mars, and the atmosphere blew most of the atmosphere into space. So eventually that will happen here, but none of us are going to see it since it's going to be a long, 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 long time in the future, billions of years. All right, so with that, I'm going to